We tap a screen and an HD movie starts playing. We click a link and a web page appears from a server halfway across the globe. We expect the internet to act like magic, a flawless, instant connection between what we want and what we get. But underneath that pristine glass screen, the physical infrastructure is incredibly chaotic. Copper wires degrade, fiber optic cables get bent, and massive data centers are constantly bombarded with more traffic than they can handle. Because of that chaos, pieces of your data, called packets, are constantly being destroyed or dropped entirely as they bounce from router to router. It's a physical reality called packet loss, and it happens every single second of every day. Between physical interference and network congestion, the journey of a data packet is inherently unreliable. To ensure your information arrives intact and in order, it relies on a strict set of invisible delivery rules. Every time a packet of data hits a router, that piece of hardware has to make a calculation in a fraction of a microsecond. When pieces inevitably go missing, how should the system react? It comes down to a harsh engineering trade-off. The network has to choose. Does it pause everything to make sure every single piece arrives perfectly intact? Or does it ignore the missing pieces to keep the stream moving forward as fast as possible? That impossible choice forces absolutely all network traffic to physically fork down one of two very distinct paths. The path your data takes dictates exactly how you experience the internet, whether your video call freezes completely or simply stutters for a moment before pushing ahead. Take the left path, and your data is using TCP, the Transmission Control Protocol. Think of it as a heavy, armored delivery truck. It is meticulous, highly bureaucratic, and deeply obsessed with accuracy. TCP is connection-oriented. It refuses to send a single byte of actual data until both computers complete a strict administrative setup. This sequence diagram shows what we call the three-way handshake. Node A reaches out with a synchronized signal, or SYN. Node B responds with a SYN-ACK to acknowledge it. Finally, Node A replies with one last ACK to lock the connection in place. With the handshake done, the real work begins. To guarantee reliability, TCP attaches a specific sequential number to every single packet, and it demands a digital receipt from the receiver for every one of them. If a packet goes missing in transit, TCP hits the brakes. It halts all new transmissions, turns around, and resends that exact missing piece until it gets confirmation that it arrived safely. You end up with a flawless, perfectly assembled file at the destination. But all that heavy administrative paperwork and constant error checking demands a huge amount of time, making this path notoriously slow. Now look at the right path. This is UDP, the User Datagram Protocol. If TCP is an armored truck, UDP is a stripped-down, hyper-fast motorcycle. UDP is entirely connectionless. There is no three-way handshake, there are no delivery receipts, and there is zero administrative paperwork before it starts moving. Instead, UDP operates like a massive, glowing t-shirt cannon. It takes your data and blindly blasts it at the destination IP address as fast as physically possible. If an orb of data drops, shatters, or misses the target completely, the protocol doesn't care. It simply ignores the loss and fires the next packet without missing a beat. By completely sacrificing accuracy, sequencing, and reliability, UDP achieves unending, unrelenting speed. These rules in the transport layer govern the behavior of every application on your device. When you download a PDF, load a web page, or send an email, your application uses TCP. In those scenarios, a single missing packet would result in a corrupted, unreadable file. You need historical perfection, even if it takes a few extra milliseconds to load. But when you boot up a fast-paced multiplayer game or jump into a live video call, the math changes. Real-time continuity matters significantly more than making sure every single pixel arrived perfectly. That requires UDP. Because UDP doesn't stop to ask for missing data, dropped packets just manifest as microstutters. The screen might blur for a fraction of a second, but it never forces you to wait for old data. The specific type of frustration you experience online, a total screen freeze versus a momentary graphical glitch, is directly determined by which protocol your application chose to use. The internet functions through a series of calculated engineering compromises designed to mitigate constant physical failures. Every single click you make initiates an invisible, high-speed dance between TCP's flawless accuracy and UDP's unrelenting speed. The seamless experience we see on our screens is the result of these protocols efficiently hiding or recovering from millions of microfailures every minute. Subscribe to Visualnet for more visual cybersecurity and networking insights.